Today I will be talking about dynamics. And dynamics studies the iterations of functions, and so today, like the family of functions we're going to be iterating is the so-called logistic math family, which looks kind of like this. And kind of one of the key questions of dynamics is what does the kind of end behavior of points look like under iteration? And so I'm going to keep this little plot going. So this is going to be our R value. It's going to map between 0 and 4. And this is going to be kind of our stable. And let's see what our stable points are for each value of R. So for R between 0 and 1, it's actually quite easy. Because our function is always less than x. So if you draw kind of the orbit diagram of points under this function, it's just going to tend towards 0. So that's the first part of our plot. It just stays at 0 between 0 and 1. Between 1 and 3, you get a slightly different picture. Where now the fixed point at 0 becomes repelling. And so you get that points tend towards, points will tend towards a kind of attracting fixed point. And this is located at R minus 1 over R, so our plot looks like this. But what happens when both of these fixed points are repelling, as with R greater than 3? What happens is that points tend towards a stable 2 cycle, and then a 4 cycle, then an 8 cycle, on and on, until you reach this magical number R is approximately 3.57, in which case it's completely chaotic, except for like smaller genes where there's a 3 cycle, 5 cycle, n cycle for any n. But for the most part, there is no attracting cycle whatsoever. That's not it though. If you measure the kind of distance between each of these little, like where it splits off, so you take the ratio of this one to this one, and the ratio of this one to this one, and so on, you keep on doing that, it actually converges to a limit of about 4.669. And that's not the end of the story yet, because it turns out for any kind of function, if you had like a family of functions that looked something like this function, it looks very similar to our old kind of functions, but it is a different family. This same number appears, and it'll appear for any kind of what are called quadratic-like maps that are symmetric around our critical point at 1 half. Quadratic-like just means 2 to 1 and kind of expanding, so these derivatives have to be greater than 1, back to greater than 1. So then the question becomes, what's the deal with this number? What's the deal with 4.669? And the answer has to do with this thing called renormalization. So renormalization is originally a tool from statistical physics. So let's dive into physics land and deal a bit with kind of, imagine these are atoms in some kind of macroscopic material. And what renormalization lets you do is treat, let's say these kinds of blocks are like your atoms. So what we want to know is kind of, as we make these blocks bigger, what happens? So let's draw our little phase space of configurations over here. And let's say arbitrarily that one atom is over here. As you make these blocks bigger, one of either, for each kind of parameter these atoms could have, one of two things are going to happen. So either they could be kind of like noise terms, like, you know, atoms and materials are always like jiggling around. But as you make these blocks bigger, the jiggling is going to matter less and less. So as you make these blocks bigger, it's going to, for anything that looks like noise, it's going to be smaller and smaller. But for anything that looks like signal, like if you're in a magnet, atoms like to align their spins so that they're all pointing in the same direction. So these blocks are going to be more magnetic than a single block individually. So if you have something that looks like signal, it's going to go this way. And as you make these blocks bigger, the flow of what's called the renormalization group flow, nothing to do with group theory, blame the physicists for that one, it's going to tend towards this specific line no matter what your individual atoms are going to look like. And so this line is called the unstable manifold, which sounds backwards. Why are points tending towards the unstable manifold? But it all has to do with this fixed point, where in the direction of the unstable manifold, it kind of is unstable. It will leave the fixed point. But in the direction of the stable manifold, it's going to contract. So what this lets you do is kind of say you only have to look at the parameters parameters that correspond to the unstable manifold to get a full idea of the full object. Like you don't have to think about the little microscopic jigglings every time you interact with the table because that's not one of these relevant parameters. So what does this have to do with dynamics? Well, we can do kind of a similar kind of coarse-grained procedure, just not in space, but in time. So we're going to take a look at f of x, which for parameters we care about kind of looks like this. And if you look at this really carefully, what you get, you kind of like spin it around a little and blow it up. You get something that looks a lot like our quadratic maps from earlier. But this one, because this is f squared of x, this one is going to have half the period of our original f of r. So we can coarse grain in time and turn our, n cycles into n over 2 cycles by doing this kind of map that sends. So we want to take a look at this function is can be some t composed with f of r squared composed with t. And so if we formally define our renormalization operator, it's going to look like fancy r of f r is equal to t composed f r squared. And this is going to sound crazy. You can explain everything about that plot just with this renormalization operator, and that's what physicist Central Feigenbaum in the 1970s proposed. He proposed 3 conjectures, all of which were proven in the 80s, that help explain all of that. The first is that this renormalization operator has a fixed point.
Who's the person you named?
Mitchell Feigenbaum. I'll explain kind of why these explain everything, but first I'm just going to write them down. The second is that the derivative of this operator has one eigenvalue with magnitudes greater than 1, and all others in the complex units. And the third one is that the unstable manifold of our system, it will intersect transversally a special space H, which is just going to be kind of all our functions where our critical point at 1/2 as an attracting 2 cycle. This is a weirdly technical one. Like we for the most part our file is just the first 2, but we need this one to make everything kind of actually go as it's supposed to. So if we have our 1/2 falling into an attracting cycle, like not just falling into, but being part of the attracting cycle, that's going to be H. And so here's the picture. We're going to draw, imagine this is our infinite dimensional function space of analytic functions that are symmetric, quadratic-like and symmetric around the critical point. What conjecture 1 says, these were all proven in the 80s, by the way. The proofs are, and I cannot stress this enough, incredibly unenlightening. They rely heavily on numerical estimates and computation. So we'll just skip right to why this matters. So conjecture 1 says we've got a fixed one. Cool. Conjecture 2 says we have one eigenvalue greater than 1 and all others are inside the complex universe. If we go back to kind of our magnetism example, little pushes in this direction are going to be kind of pushed back into the center. So that's going to correspond to the stable manifold is going to correspond to eigenvalues with magnitude less than 1. And the unstable manifold is going to correspond to eigenvalues greater than 1 because little neighborhoods get pulled in this direction and squished in this direction. So what we have is a 1D unstable manifold. And the stable manifold being of codimension 1. Which you can basically think of as being infinity minus 1 dimension. And for condition 3, we have our other manifold H that we know crosses the unstable manifold. So if we look at our logistic map family in this kind of space, it'll look like a 1D manifold. If you don't know what a manifold is, it looks like this. Like that's all I'm going to get into. So our logistic map family is going to be here. So after enough iterations, like you imagine, this is the first iteration, second, third. The line here is going to hold because it's going to hold along the stable manifold towards our kind of unstable manifold. So what this ends up mattering is that only one parameter actually matters, the path, like the location along the unstable manifold. Because we're dealing with the kind of macroscopic limit again after a lot of renormalizations, which is what you'll be able to do when you're really close. You have a function here that's really close to this r approximately 3.5 seconds. And this intersection, you can trust me, r equals 1 plus the square root of 1. So the action of our renormalization operator in small neighborhoods around here is just going to be to stretch them by a factor of r Feigenbaum delta. Oh, I didn't mention. This turns out to be our delta, which is about 4.669. This is why it's called the Feigenbaum delta. So, yeah, so if we have, okay, so let's just kind of picture our drawing over there and just superimpose it on our phase space over here. So there's going to be a 2-cycle, and that's going to be 4-cycle, 8. This is just for like visual reference. Each of these, imagine like our R guys are going to correspond to everything. If we just take the segment that corresponds to some cycle 2 to the n for n sufficiently large and iterate our renormalization operation, it's going to get pulled towards the center. And if it's really close, it's going to stay in this kind of location around the unstable fixed point. So what it's going to do is stretch it out by a factor of our Feigenbaum delta. So it'll map our 2 to the n kind of functions to our 2 to the n minus 1 functions. So this space of 2 to the n minus 1 functions is going to be 4.669 times bigger in a sense than our space of 2 to the n function, and that's why if we go all the way back to our picture over here, this is 4.669 times bigger than that, and that approximately, and it's only going to get better as you approach this value. So what you get when you end up crossing it, what happens, the boundary between order and chaos is really interesting because it's a phase transition. And quite literally, it is a phase transition. If you go back to our kind of magnetism example, where you have a magnet, you heat it up, you heat it up, you heat it up, and then once you cross the Curie point, it's suddenly no longer magnetic. That corresponds to, if your atom's up here, it's going to tend all the way up to that kind of end behavior. It's down here, it's going to go all the way down to this kind of end behavior. And so there's this phase transition as your atom crosses the stable manifold. And so as our parameter crosses the stable manifold, it goes from eventually crossing H to never crossing H ever again. And that's why we suddenly no longer have a cycle of length 2. So that's basically the mechanism. Does anyone have any questions?
So confused about the dictative number and where it comes from.
So it's this derivative of the operator. It just happens to be the only eigenvalue that's greater than 1. Yeah.
Why that equilibrium?
It just is. It's just one of the constants. It's like why is pi pi? Why is EE? This number is like pi for dynamical systems.